I will, of course, start by mentioning that the last time we met, our first day back from spring break, obviously, you took a test. And so I haven't got a chance to look at those too much. Actually, I did get a chance finally to do last night, look a little bit at the first problem. And it seemed to go well. And if you guys remember the first problem, it was the liquid that was in the cup. And all of you guys had different liquids in different cups, and some of them were brass, some of them were aluminum. And this class, I think it cooled down. Yeah, and so, yeah, because the other class, I think I heated it up. And so anyways, you guys were supposed to find out, you know, how much extra volume there was in there. So anyways, you seem to have gotten the point of that. So anyways, that's a long way of saying I will grade them this weekend, expect them back on Tuesday. We'll get you the grades on Tuesday, and we'll kind of go over that. Meanwhile, we will continue on with our optics. And I say continue on, but it's kind of been a weird start. But now that we're really into and back from spring break, we can, because as you recall, we put the test off from before spring break to after spring break. And as a consequence of that, we went ahead and we started the optics. And so we already really had the first lecture on optics and the first chapter on optics. There's one minor thing to add. I shouldn't say minor. I mean, it's important, but it's, well, maybe it is kind of minor, but it's an important minor idea of the geometric optics. And so I thought I would begin today by saying, do you remember 16 days ago we had a beginning lecture on optics? And just in case you don't completely remember that, I decided maybe writing the title and reviewing what we talked about might be a good place to start. So chapter 35 was our first chapter on optics, and the title was The Nature of Light and the Laws of Geometric Optics. And so our first two chapters in optics are what we call geometric optics. We'll get into wave optics on the next two chapters after that, just to kind of give you some forewarning there. But if you remember that discussion from, like I said, 16 days ago, we started with the nature of light. And what we said is you can view light as either made out of waves, or you can say they are made out of particles. And so when you get a chance, if you haven't already, that's what you'll see as you review your notes, as you get ready to do your optics. And so this weekend, as you start to do these homework problems, that's what you're going to go back and see. And so I'm hoping by me saying that, it kind of brings back, oh yeah, I remember that discussion and the analogy I gave, and trying to say light is really both at the same time, just like you are both a student and an employee at the same time. But of course, you know, given the experiment, like right now, if I made an observation, I would probably say you're a student because you are in a classroom, you are taking notes. But other times and other experiments may lead to other results here. And so that's what we meant by this wave nature of light. If we thought of them as waves, we said that they were made out of what? What was waving? Electric and magnetic fields. Good. And so that was the part that was waving. If they were made out of particles, we just gave them the word photons and said, well, that's what light is. Light is not like it's an electron or a proton or an atom. It's its own little particle, and so it's a photon. Then after that, we got into the laws of geometric optics. And if you recall, there were two of them. The first one, we called it the law of reflection. And what we said is if you took, say, a mirror and made a perpendicular, a normal line, and were to shine a beam of light at some incident angle, which we labeled as theta 1, it reflected off, and we called that theta 1 prime. And we even plugged it in and turned it on. And so again, maybe as a quick review here, you might remember us taking our mirror. Here's the polished surface. Here's the little laser beam. Maybe the chalkboard lights make it a little too bright. But then I would draw maybe something like that. So there's normal to the surface, and so this being the incident angle, and let me point out, notice the incident angle is measured from the normal. And so that's theta 1, and this would be then what we would call the reflected angle, and what we tried to argue was that theta 1 equals theta 1 prime. And that was the main point of law number 1. And we're going to use that a lot as we get started into the next chapter. Law number 2, which we called the law of refraction, was a little more involved. And 2/3 of you have done the lab on the refraction one, and the other third of you will do it today. It was discovered by Snells, so we often refer to it also as Snell's Law of Refraction. But what it said then is that when you have a beam of light coming in and hitting, say, a piece of glass, what will happen is as the beam comes down, so we will still call this theta 1 for the incident angle, but when it hits, the speed changes. And we labeled the speed in the glass as the speed in the vacuum divided by its index. And so this is the index of refraction. And it is basically a number that tells us how much does the light slow down. If you remember looking at some of these, we said, well, if this was a vacuum, the index would be, okay, good, 1. If it was, say, glass, it would slow it down by 50%, so its index would be 1.5. And I think that's what you guys saw in the lab for that beam that we did for the piece of glass. I guess we also in the lab did water, got 1.33. We did not do air, but we did talk about the air, and it is small, but slightly greater than 1, so the air slowed down a little bit. But keeping in mind then that that's what happens as the light slows down, we made the argument here that if you had a beam of light coming down, this lower edge in the beam of light would hit first, slowing it down and making it bend. And in this case, bend towards the normal. We called that angle in there theta 2, and we went through a derivation by Snell that said the incident angle theta 1 and the refracted angle theta 2 must be related mathematically in a more complicated way than this one. Maybe I should put a box around it because there's law number 1 and there's law number 2, and those are the answers for all the homework problems in this chapter and next, believe it or not. We'll build on this in the next chapter with some much more complicated formulas, so we'll probably never come all the way back to these basic 2 formulas, but that's what I tried to get across in the first lecture, and hopefully did, and hopefully this little review reminds you of that, because soon I want to just get into doing some examples and then move on into the next chapter here, and start applying this to forming images and building telescopes and building microscopes and using the bending of the light to control the light and make things bigger or smaller or closer or further. And that's the idea coming up here. Oh, I guess I could turn the lights. Well, I was going to turn them back on, but I guess now I want them off because I wanted you to see Snell's law. So this is the law of reflection. The law of refraction would be something more like this, where, and I'll move it down a little bit, But if I were to take then and kind of outline this glass block, which is what you did or will do in the lab today, you will see that if I draw a normal, and maybe even draw where the light is going after it goes through the block. If I lift the block up, again, like you guys did in the lab, I can draw the beam coming in and then the beam going through the glass, and you will hopefully see that right here, this is the theta 1. This is the incident angle. This right here then is the theta 2. That is the refracted angle. And so as the light comes in, it bends. It bends, in this case, towards the normal. And I think you can see that for any case that you would go from a smaller value to a bigger value of index, which in this case, from air into glass, if this N2 is bigger than the N1, what would that say about theta 2 compared to theta 1? Yeah, it would bend and get smaller. So theta 2 must be smaller. And sure enough, I think you can see that. But I also want to point out, which we didn't get a time to look at last time, is what about here? When the light is leaving. You see, anytime the light changes its index, there's going to be a slight bend to it. That's what Snell's Law is saying. It is saying, look, if you change your speed, there will be some bending. And of course, how much bending depends on that change in speed. But in the second surface, we are going from a higher index glass to a lower one. And so if we come back and look at here from a higher to a lower, that means this angle theta 2 has to be bigger, and so we say it bends away from the normal. And again, I think you can see that when I draw it like that. And in this case, this bends back to the same angle that it originally had. Kind of makes sense because it bent in and then bent out by the same amount. And these two are parallel. Now, that may not always happen because you may have something that looks more like this. But I'm hoping you will notice that as it goes in, there is a slight bending towards the normal. And then as it comes out, there is a bending away from the normal. But because this surface, and maybe I should try and draw a normal over here. But because this surface is not parallel to that surface, it is still down. So in this case, the beam coming in, bending towards the normal, is down. And this coming out is bending away from the normal, which also is down. And so clearly the direction we have now is very different than the direction it originally had. And so some of the questions you'll be asked on the homework will be, find the deviation angle. Now, what angle is it headed now compared to what did it start at? And I like to label it with a D. What is that deviation angle? But hopefully you can see that it would be a series of geometry and Snell's Law. And that was what I was trying to get across to you, again, 16 days ago, that our two formulas here are not too complex, but they do, when added to geometry, make for some challenging problems at times as we got to work through the geometry. This one here, I think, is a homework problem as well as a lab problem that, again, 2/3 of you already did, but it asks for what is the lateral displacement. This one clearly has the same direction, but it is displaced a little bit. And so you guys in lab were asked to do it, and I know the author does a good example of it, number 4, and it's also a homework question. What's the lateral displacement? Whereas this one is an angular deflection. In fact, I thought I would bring these out here because if I were to hold something up like this flashlight, you guys, can you see it? Sure, why? What makes you see the flashlight? Yeah, well in this case I would say the light comes in and this blue strip means it reflects the blue light. So we start with white light in here, the light comes off, it reflects, but only blue reflects. And so the reds and the greens get absorbed and you say, hey, that strip is blue. And this one, well, it's black, meaning it absorbs all of them. So you can see the absence of the light, you can see just one color of light. Seeing things because they reflect the light, I think is a little bit easier to understand than, can you see this glass beaker? Yeah, and you laugh and go, yeah, of course I can see it. But why can you see it? Does the light reflect off of it? And you might say actually some of it. But the light is affected still, right? This is more of a description of Snell's law here. And the light is deformed. And yes, there is a small amount of reflection. In fact, I could maybe even see some light coming off of there. So yeah, there is a little bit of reflection. But there's a lot of refraction going on. And so the light that is coming from behind, the light is coming from the side, it gets bent, it gets woven around here. And so that effect tells me there's something here. Fair enough? Because this is an empty beaker. This one, of course, is filled with water. But can you tell it's filled with water? I think you can, right? Now, remember, the water has an index of 1.33. The glass has an index of about 1.5. And so there is a small difference between the glass and the water. But isn't the surface between the glass and the water kind of disappear? Can you see it? Some of you are saying yeah, some of you are saying no. It's kind of hard to see the surface between the water and the glass. I know you can see the surface between the air and the glass really well, and I know you can see between the water and the air up here, and certainly down here. And so because of that, the light is affected. And this is always a fun one to watch. Can you see me holding what we call a water marble? It is just some jelly filled with lots of water. And now what's nice about it is this has an index pretty much of water, 1.33, because it's 99% water. Can you see the water marbles in here? Sure. Can you see them now? And so when we match the index, there is no deflection or variation of the beam of light, and hence our eyes don't pick that up. And so it's the controlling of that light is really the basic physics we're trying to get at to say, why do we see the things we do here? If I scoop in here, there they are. Pour them back in, there they're gone here. And so it makes a nice little demonstration of Snell's law here and the movement of the light here. All right, well, there was one last thing to show you in this chapter that I just kind of ran out of time to get to, and that has to do actually with this part right here when the light is coming out. Because if you will notice, going in, it always bends towards the normal. All right? But if I give myself a little more working room, say here, and I take this prism, maybe I'll power these lights back down. But if I twist this a little bit, and a little bit more, and a little bit more, and I focus on this beam coming out. Again, notice how the one coming out bends away from the normal. And so I want to emphasize this would never happen going into the glass. But coming out of the glass, what could happen is we could eventually get 90 degrees. It's gone. The refracted beam, where did it go? Yeah, and don't forget in all of these, and maybe you saw it when I was setting it up, there's also the reflected part of the beam. But as you'll see, say right there, you do have a reflected beam. And I think, is it dark enough in there you can see the reflected beam? And you have a refracted beam. And if I turn this just enough, even more, not quite to what we're going to call a critical angle, but I'm getting close to that critical angle. What I'm beginning to see is I'm beginning to see that this exited beam, the refracted beam, is getting less intense. It's getting dimmer. While the reflected beam is getting brighter and brighter. And right at the transition, that is, well, let me back it up just a hair. Can you just barely see this red beam coming down here? When I put my finger there? Yeah, well, that's why I put my finger there, so you can see it better. But it is really dim. I'll do the house lights. Maybe you can see it even better there, right? But if I go just beyond that, at 90 degrees, it completely goes away. Kind of makes sense. It's going back into the glass. It is why we call this then a total internal reflection. And so the last discussion for this chapter is really this total internal reflection. It is what you might call a refraction taken to its extreme. And notice it can only occur when you are going from a high index into a low index. Let's do a quick numerical calculation, but as you will hopefully see, as I mentioned earlier, partly joking, partly serious, this is the answer to all of our homework problems here. And so we call this total and internal reflection. I kind of wonder if they shouldn't call it total internal refraction, because it really is in a refraction taken to its extreme. Yeah.
Did you say that it went away when you turned that to 90 degrees?
Not 90 degrees. I didn't, but when I turned it, yes. So I'm not saying 90 degrees. In fact, I want to go through some math to show you what the number is. Is that what you meant?
I thought you said 90 degrees.
Oh, I'm sorry. What I know what I did say. What I meant was, and what I was trying to say is, the refracted angle is 90 degrees. And so right there, if this is the normal, then the refracted angle, which you can't see anymore, is 90 degrees. So theta 2 is 90 degrees. That's what I was trying to say. Okay? And that's going to be an important part here in my calculation, because if I put down n1 sine theta 1 is equal to n2 sine theta 2, then to find this critical angle, and there we go. Sound back on? Got cut on that thing again. All right, but the critical angle is my question. What angle would I have to come in to hit it? And so this piece of glass, that's, maybe I'll start with a light bulb inside the glass, something like this. A beam of light that comes up to here gets out, meaning this angle is less than critical angle. but there is some angle that is at the critical angle and no light gets out there. And for that matter, angles greater than the critical angle do not get out. And so again, maybe it's worth seeing here by powering the lights down, but if I turn it back so that I am less than the critical angle, of course, that's what I mean. Some light gets out. But if I turn it right there till it just disappears, that's the critical angle. If I go to angles greater than the critical angle, you will see also the light doesn't get out. And so the critical angle is not the only angle where the light can't get out. It is just the smallest of the angles where the light can't get out. And so every light coming at an angle greater than the critical angle, you would say, is trapped inside of that piece of glass. Numerically, I could calculate it by this, saying set theta 2 equals to 90 degrees. That's the 90 degrees that I came up with. So the critical angle would be calculated by taking the ratio of the indexes. In my case, I am starting in glass, so that's about a 1.5, and I'm going into the air, which, depending on how much accuracy you want, I'll just put a 1 and say it's 1 divided by 1.5. And that would then be the critical angle for this glass piece, which, out of curiosity, inverse sine of 1 divided by 1.5 is about 42 degrees here. So as long as my incident angle is 42 degrees or greater, no light will get out. Now, the real usefulness of this is what would happen then if I took a piece of glass and made the glass thin enough that it can be flexible, and I were to shine a light at the end of this fiber optic. What would happen to it? And the light comes out the other end. So the light is trapped inside. And I think you are a little familiar with fiber optics in the sense that we use this all around us as we communicate, as we make phone calls, as we do our internet. We've got, thousands of these laid around here. And we've got the main network right here, it goes right up to Santa Barbara, right along the railroad tracks there. You can even see, when you get there, it says, "Do not dig AT&T fiber, call this number." And of course, there's also the other utility lines. There's the gas lines and natural gas and petroleum, and they all go up and down the coast there. And this one actually goes up to Morro Bay and then under the ocean to Hawaii and under the ocean Hawaii to Japan. And so when you're surfing the internet, that's where those little flashes of light, and they're just traveling those thousands of miles in these little fibers. Yeah. Thin. No, I know. Glass, I think, is hard to imagine, but let me do this. If I had a piece of metal that was this thick, this tall, and this long, could you bend it? I take that same piece of metal and I make it thin and I make it into a wire. Can it be flexible? Right? So if you've ever looked at a wire, they're often made out of 100 little tiny ones wrapped together, right? That's what a wire is. So it's the size that makes it flexible. Glass does the same thing. I know it's kind of hard to imagine glass being flexible, but glass is flexible. I even have some here, but before I get there, I'll do the cheap version of the fiber optics.
Why did you say it had to be flexible? What does that help us? Why can't it just be a straight up? Oh, because anyways would have gone through.
Well, you want to be able to lay it, right? I mean, in our case, we want to be able to take this fiber that comes out in our computer network center. We want to be able to then string it through the building walls, then bury it underground, make it go along the railroad tracks and go to UCSB, because that's where our fiber goes, because then UCSB gets onto the main backbone, and so their fiber runs along under the, the railroad tracks or whatever. So you need that flexibility, and then you get to the ocean and you want to lay it down and strung along the bottom of the ocean. Yeah.
So then there's still a limit of bandwidth you can get through that?
Now, if you're asking if there's a limit to how much I can bend it, well then yes, right? See, if I bend this too much, then this angle is greater than 42 degrees, then the light is going to get out, right? And so, again, maybe the best way I can start with a picture of some fiber optics is maybe to turn off the room lights again and take a little flashlight and take, I'll shut at least one of these. Maybe we'll make a little. I think that'll be. But if I just take this piece of plastic, and the plastic is nice because it's not really designed to be a fiber, and it's got so many impurities that some of the light reflects off and you can actually see the light. In real fiber optics, you would not be able to see it, right? The light's not coming out of it. But I think if I point it at you, you will begin to see that most of the light does follow along and come out the other end. If I take that same piece of plastic and I heat it up and melt it, you can kind of see the same effect, that the light travels along and eventually does follow the curved path. Now you can see in this one that you can actually see quite a bit of light coming out here. So this is a significant bend, and a lot of the light does end up going greater than the or less than the critical angle, and then it comes out here. But there is your fiber optic. If I kind of turn the room lights back on, this one is off of our computer network and literally is a connection between
How does it not mess up the information coming from
a computer. Hang on here, let me show you. But these, unfortunately or fortunately, are small that you can't see them. Remember, we want them flexible. So the fiber itself is probably the width of a human hair or smaller. Okay? Then they're laid in plastic so that you don't break them. And so this, looks like it has a diameter of about 1 millimeter. That's not the real fiber. The real fiber then comes out that end, which is about the size, like I said, of a human hair. So I wonder if this will be bright enough to see. But on this end of it, there's a whole series. I don't know if you can see, but it looks like there's about 15 little tiny holes there, 15 fibers that run through. Some of them come out here and, well, I guess like that. So all of the, maybe 20 of them there, with about 5 here and 15 here connected together. And so if I turn off the room lights, and maybe I'll point this towards you. Can you see any light come out if I shine it on there? Was that a yes or a no?
Yes.
Okay. Yeah. Wonder if I can see it better with this. Yeah. And so as I kind of just move the light in front of the laser beam, you'll see it go into the fiber and hopefully come out of the fiber. Am I getting it? Yeah. And you can see little flashes of light. So again, kind of hard to see because they're so small, but hopefully you're getting the idea and the design of the fiber optic, and that is to trap the light inside and send our signals that way, and then the pulses. And you mentioned bandwidth, and what you really meant by that was not so much did it bend, but how many pulses you can put every second. And so a good fiber can do, I don't know what the current number is, but I'll say around 10 billion, flashes of light every second.
But
so
then if some light are leaking out, then that messes up the information that you're sending.
Right, that's why this. Now, careful. You said mess up. I don't think you mean mess up as much as reduce the signal. The signal's still there. The pulses are still there. The information is based on the frequency of the pulse. Okay? So if I lose some light along the way, it's just not as strong when it gets to the other side. That's the beauty of digital communication. The quality does not diminish at all over a long length. As long as you don't lose all of it, or it gets all washed together. So there is a limit to this. This would not make a good fiber optic. There was too much loss. But when you saw this one, did you see any light coming out the side of these? No, no. It really is of good quality and trapped inside of there. Now don't get me wrong, it can only go so far. And so when you really build a fiber optic network, you have a fiber, and then at some point you have to put a repeater. And so the light has to come in here, and you have to have a new laser. And so the flashes of light come in, trigger some electronics, and a new flash of light is created. And it's just a repeater, meaning it doesn't have to think much, it just has to flash the laser at the same rate. But by here it's got real dim, and then it just makes it brighter again. And so the signal is repeated. And so you just lay these across the ocean floor, and then we can get our signal from Morro Bay to Hawaii fairly easy. Just make sure you put enough energy in there so you don't have to go down and do maintenance on it. And so I think they use a little radioactive pack for its energy, kind of like NASA does on the satellites, and so it's, should keep going for 30, 40, 50 years or something like that, and everything works good. Nobody has to touch it.
How much do those repeaters actually slow down the signal?
Yeah, I'm not sure. I'm not sure on the number, but yes, then they slow it down because now we have to take the light, convert it to electronics, which then converts it back to light. Yeah, and
Is that why you get the bigger latencies and stuff?
the bigger what?
Latencies, like
Yeah. Yeah, it takes a while for this, information to go. It's already taken, every foot of fiber is taking about 1/1000th of a second. And then every repeater, I don't know what the number is, but it's going to take even longer. So there's a delay for the information to go across the world. Nothing like 1850 for information to go across the world. Wasn't the Battle of New Orleans actually after the Treaty of 1812 signed? Yeah, because nobody got the news. You sign a treaty, and 3 days later you have a battle, and a month after that you get news. Oh, the war was over. Well, the war was over before you started the battle. Oh, well, it would have been good to know. Yeah.
How far can you typically get with your cable before you need a repeater?
I don't know how far they get today. I know when I worked on some of these, back when dinosaurs were still walking on the earth. And that's why I said 10 gigahertz, because we were getting about 1 gigahertz when we were working on them, and I'm pretty sure I've read at one point they were at 10 gigahertz, so that's probably even old information. But we were going about 1.5 kilometers before a repeater. Yeah, yeah. And I know there was, I almost ended a career ended up in the career of working in the fiber optics, because there was some big money, and maybe there still is, I don't know how clean they are, but getting the glass fiber is very clean, because your loss is really contributed to the imperfections that are in your fiber. And so by having really good quality fiber, you can get rid of these repeaters, which again speeds up the network incredibly fast. Yeah, yeah.
So like the new Cat 6 cables have a certain rating of like speed or like how much information they can carry. Does that have a direct relation to like how efficient the wire is? Like you were saying, you were doing 10 gigahertz.
Right.
Does that have a direct relation to the rating on like your Cat 6 cable that says it can carry 1 gig, 10 gig, 100 gig?
Yeah, yeah, that is that is the rate, 10 gigs. You know,
okay.
How much can you?
They've got cables that do
1,000
gigs of information.
a terabyte,
Yeah.
and that's not any parallel processing. Oh, okay. So yeah, my numbers are way small then. If you're talking about a terahertz, yeah.
I don't think we have the ability to push it yet, but we can carry it.
Oh, okay. Oh, I see. Okay. And because there's other issues. You gotta turn the laser on, off, and on. And so you gotta have the fiber that has the ability to carry it. Then you also have to have the laser that can go on and off that fast. And you have to have the detectors on the other end that can detect that fast here. So everything in the network has to, there's always some part of it that is the missing link or the slowest link in there. And throughout time, that changes depending on how technology advances. Which part is the slowest part of the network? Yeah. So there's, like I said, your basics of your optics, and obviously the fiber optics is a good first illustration of why do we care about this. So with that said, let's do a couple of examples here. I put number 43 as what I thought would make a good first good example to calculate. And so let's look at number 43. Actually, I'll start this overhead on. I think there's a little figure in number 43. And if you guys remember from the Thursday before break, and I wasn't here, I learned that you guys loaded a PDF version here of the book on here. So, all right. So that's, you said dangerous?
I said Lester did it for us.
Oh, Lester did it for us. Yes, yes. And Lester's dangerous. I understand that. And so let me pull up the PDF. It'll have the picture and the question. That might make things a little bit easier than what I've been doing, which is just kind of calling up the picture. But somewhere in here, let's look at number 43. Number 43 doesn't have a picture, but now I got to remember what I did with it. Oh, I was looking at it. Here we go. And so I guess the questions would be at the end of the chapter. Ooh. Okay. Yeah, seemed long doing it that way. Glad I don't have to do the homework. All right, but so anyways, here's 43, and so there's no real picture to it, but what does it say here, and what is it focusing on? Well, it is our first Snell's Law, if you will, and it says this. It says a narrow beam of light is incidented from air, okay, into the surface of glass that has an index of 1.56. Find the angle of incidence for which the corresponding angle of refraction is half of the angle of incidence. Okay, and so the idea drawn in a picture is something like this. We have air, we have glass, we're sending it in at some angle theta 1. The fact that they told me it was air was kind of the clue that they want me to use an index of 1 or 1.0003 if you like. Okay? But there'll only be a few times where 0003 is going to be relevant to our numbers, and this won't be one of them. So we're going into glass, which they say is 1.56. We know that since we are going into glass, it will bend towards the normal. And so this is what we call theta 2. And they want it set up such that theta 2 is half of theta 1. That's the question here. You know, what angle is it? Well, it's a straightforward Snell's Law. Sine theta 1, or n times theta 1, sine theta 1 equals to n2 times sine theta 2. I'm going to write it as a 1 for index 1 because we're starting into air. I'm going to write this as the sine of 2 theta 2. Only because if I'm going to solve this, I'm going to have either double angles or half angles. And I think I remember the double angle, but I think they also, yeah, gave it right there. Okay, so that'll be helpful. I was going to go to Appendix B, but they already gave it. There's the index that it goes into, and then there is the sine of theta 2. If I then do the trig identity, is it 2 cosine and sine? Yeah, so 2 cosine of theta 2 and then sine of theta 2 equals 1.56 equals sine of theta 2. Then it actually worked out without too much effort to say cosine of theta 2 is 1.56 divided by 2, and then I can get out my calculator and solve for what is theta 2, which would also be theta 1. So inverse cosine of 1.56 divided by 2 is about 38. What did I say here? 38.7 degrees, which of course means theta 1 is twice that. And so we're looking at an angle at about 77 degrees. So if you shine this thing in at about 77 degrees, you will get about half the angle, which we could probably even see that right here if we kind of roughly set this up, because the numbers they gave us are probably pretty close to these numbers. This is probably more close to 1.51 than 1.56, but that would probably be what they're talking about. 70, well, maybe 77. That's pretty close to 80 degrees. So maybe closer to that. But there it is, 77.5 degrees. There. And then this angle right there, if I can write on that, would be half. I hope that comes off. Oh, good, yeah. And so there was problem number 1. Let's jump over to 53. 53 takes it a step up here. And let's read that one. And then they do give a nice little picture of a block and say, all right, let's look here at 53. And 53 has a couple pieces that comes together here. Here we go. It says a light ray of wavelength 589 nanometers, which, if any of you care, that's going to be yellow. We're going to use that actually wavelength a lot in the lab. It's a wavelength that is nice to calibrate our equipment from, so you'll get used to that number. But a light ray of wavelength 589 nanometers is incident at an angle theta at the top of a block of polystyrene, as shown in the figure. A, find the maximum angle theta for which the refracted ray undergoes total internal reflection on the left vertical face of the block. Okay, so looking at this picture, and maybe I'll draw one here, and this comes in at some angle. Then it strikes the vertical face on the other side of that glass block. What happens there could have a total internal reflection. And they're saying what angle would do that? What is the maximum angle? So before we try to do any calculation here, let's see if we can...
What incident angle or what?
Oh, I think it said what maximum incident, right? Find the maximum angle of theta.
Okay.
So that is the incident one. So here is the ray coming in at some angle theta. In fact, maybe we should just, for discussion, talk about what if the angle theta was small, like this. Well, when the ray comes in, whether it's at a big angle or a small angle, which way does it bend? Towards the normal. So what does that mean about the incident angle on the vertical face? Yeah, that would be big, wouldn't it? And so what I'm trying to say is small incident angles on the top result in big incident angles on the vertical face. And it's those big vertical angles that undergo total internal reflection. So there would be a good chance that this one would be total internal reflection. So for the light to come out on the vertical face, I would want this angle to get bigger and bigger and bigger and bigger. And I think that's why the author uses this phrase, find the maximum value of theta for which the ray undergoes total internal reflection. Because small angles, it definitely will. There's no doubt about it. Small angles will. The issue here, though, is as this angle becomes bigger, and in fact, maybe I should draw the biggest angle of all, which you might call it 89.9999999 degrees. Then that's going to come off something like this, making the incident angle on the vertical face smaller, and of course hopefully small enough that it is below the critical angle so that it can go out. And if it goes out, it would do something like that. Again, bending away from the normal as it goes from the glass out into the air. Okay? And so that's why the problem says find the maximum angle. Find the maximum value of theta for which the total internal refraction occurs. All right, well, maybe we should start there. What is the critical angle? Yeah, I guess we kind of already did it. Well, this says polystyrene. I don't know if it has the same index. Have you guys already looked it up? Or no? All right, so let's calculate that. Remember, N1 sine theta 1 is equal to N2 sine theta 2 at critical angle. The refracted angle is 90 degrees. And so our little formula we had, is it still on the board? No, but our little formula we had for critical angle a few moments ago was this. And so this would be the inverse sine of, and this is what it's going into, so it's going into air. I think it's air. Did they make that ray wavelength incidented on the top? Well, I guess they didn't explicitly say we were doing it in the air. But if we read part B says, well, what if you did this with the block submerged in water? And carbon disulfide? I just happen to have a bottle of that. Yeah, I wonder what carbon... What is it? I wonder what carbon... anyways, that'll be for your chemistry teacher. What is carbon. And maybe we do. Maybe it is common, and I don't know what it is. But what's that dry cleaning stuff? Tetrachloride. Yeah, okay, that's what was going through my mind, but that's not it. Anyways, but I'm going to go with the idea, even though the author didn't explicitly say. I think they're implying that, hey, we're talking about air here. All right, so let's do a calculation. I do need to look up, what was this? Polystyrene. And so flipping back a couple of pages, they gave me the index. Hopefully they gave me the polystyrene. Here it is, 1.49. And so it is very close to what we did for glass. And so I bet it is still the 42 degrees here. So inverse sine of the reciprocal of 1.49 and 42.2 degrees. So that would be the critical angle. And so again, to answer this question, I'm going to set it up so that this is right at critical angle. Okay?
So that nothing will come out, right?
Well, okay, and so geometry is going to work backwards to find out what angle does this have to be for this to hit at 42.2 degrees, so nothing would come out. Meaning then, for any angle greater than that, it would come out. Fair enough? All right. It looks like some of you are seeing it now. Good. But I'll keep going until all of you see it. But let's keep working on this. If I then continue on, what's that angle? Okay, so I'll subtract 90 from that and get my 48, or a little more accurate, 47.8 degrees there. So then, and if I can, I'll go ahead and erase this one here and say, okay, this is the refracted angle as it comes into that side. So I'll apply Snell's Law, or the law of refraction, whatever word you want to use there. For some reason I like Snell's Law, so that's probably what I'll say here. But let's apply this equation to this boundary, the top boundary. And when I apply it to the top boundary, again, the light is coming in from the air, index 1. The angle is what I'd like to find. What angle do I need to come in so that when it hits the polystyrene, it comes out at an angle of 47.8. And
why do you switch your N1 and N2s when you're doing the critical angle? Like N1 is...
whoa, okay. I wouldn't call it I switched them. N1 is where it starts. N2 is what it goes into. So when I was on the vertical face, it started in the polystyrene and went into the air. But when I'm doing it on the top, it starts in the air and goes into the polystyrene. Right. Okay, so now getting my calculator out here, 1.49 times the sine of 47.8 gives me, oh good, some more of you are seeing it, 1.104. Should I keep going? So what if I do inverse of sine of 1.1? I get error. Domain error. Oh, so what does that mean? Does it mean I can't do it? Does it mean my calculator needs batteries? What is this ultimately saying? The biggest this angle can get is 90 degrees, right? And I put in the sine of 90 degrees, I would get a number less than that, right? So basically what this is saying is not so much I got an error on my calculator, although I did get an error on my calculator, but more than that, what it's saying is this angle, for this to occur, the angle would have to be greater than 90 degrees, right? I can't get an angle greater than 90 degrees. So what that tells me is that any and every angle, or the maximum angle, is 90 degrees. That's what it tells me. There's my answer. What's the maximum? 90 degrees. And so be careful here. Obviously the computer is not going to tell me, or calculator is not going to tell me 90 degrees. And so make sure you kind of remember what the calculator is trying to do for you. But in this case, it has told me it is 90 degrees. And maybe that makes sense if we do this in reverse. What if we were to actually put a ray in at nearly 90 degrees? Wouldn't that just be Snell's Law in reverse? Wouldn't that then just come out here at the critical angle of 42? And I think that's why some of you saw this from the very beginning. If that's at 42, then what's this incident angle here? 48. So the smallest angle you can ever get on this vertical face is 48. And 48 is already bigger than 42. No light is ever going to come out that other side. I don't care what angle it is. And of course you can lose that in the math here when you get to this point and go, what the heck is that supposed to tell me? Okay. And so this is kind of interesting that, hey, there's just every angle is going to hit at critical angle. In fact, let's take that one step further. What would have to occur then for it even be possible for light to ever come out on this side? This critical angle would have to be what? What if this critical angle was, say, greater than 45? What would that say here? Less than 45? Which is less than the critical angle, and then it can come out? And so if you're kind of catching the optics here, and the physical meaning behind this is that if we are going to have a chance of the light to ever get out, we've got to have an angle up here that is greater than 45. Fair enough? So that this angle here can be less than 45.
You get that by shining through another side of the box?
Oh yeah, don't get me wrong. We probably could have done it this way. Put the ray in here, let it bounce off there, and then it'll come out. Is that what you mean?
Yeah.
Oh, sure, sure. So I'm not saying any light doesn't come out. But what I'm saying is any light that comes in the top will not come out over here. And then it's going to do a bounce and then come out over here.
Light comes out of glass box.
Yes. So light does come out. I'm not saying that, but it doesn't come out in this fashion. In fact, maybe I should have brought one in here. We had a perfect one in the lab, but I didn't bring one. But if I take this glass block and I put something right here, like my finger, and I look on that side, I can't see my finger. If I look over here, I can see my finger. But only when I look over there, I cannot see my finger. Yeah.
Is it possible to trap the light in circular?
No, because if it got in, there is some angle then it can get out.
But is it possible though to like theoretically to manipulate so that the light just stays inside?
Sure. I mean, let's try this. Can you see that one? Is it dark enough? to see the light bounce, 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 bounce. Of course, in this case, it does come out here on this end.
So if it's moving circular infinitely, then you can take it out and the light will still be there.
That would be so
Hey, so what? What?
So if it's moving in circular infinitely, right?
Yeah.
Then you can take it out and the light would still be inside moving circular.
Without the light source.
Yeah, take it with you.
Oh, yes, yes, and you guys hopefully will see this in your lifetime. I don't think it'll probably happen in my lifetime, but it would be great if we got away from these computers that are all silicon and electronic based. We really should get to an optical processor and optical storing memory. And there are many labs working day and night of trying to trap light and store our memories in there. And there is some really good optical memory that has come a long way in the last decade. Super expensive, exactly, and so you don't see it yet. But we are on our way to work away from electronics. Electronics is old school. It's dead. In fact, most of the devices you have already moved away from electronics. They're probably more spintronics. You wouldn't have as much memory on your hard drive without spintronics, and so they've already, most of your stuff is away from electronics and onto spintronics, but not really to the optical side of things yet. But you'll see a major revolution when we get to optical processing and optical memory. Yes, exactly. Yes, exactly what you would be doing, because that is the next big wave, and the big wave after that is the quantum computing, and a lot of people are working towards that. And
they're like there's like a group working on quantum computing.
Yep.
Working on it.
Yeah, and it's going to take it's going to take a while. I know technology goes fast sometimes, but quantum computing, I don't know. I don't see it really happening in my lifetime, maybe in your lifetime there. And then some of these quantum memories are fascinating. I mean, you could take a memory chip the size of a coin, and it could store all the information that is stored everywhere on every computer in the world right now if we got quantum computing and quantum memory going. David, did you have a question? No. No. Anyways, if I go further with this question, now we can begin to see why the author has thrown this into you. What if it is surrounded by water? And so let's change all this and recalculate based upon water. And so I'll eliminate those numbers there. And I will change this calculation here and this calculation here and say, all right, well, let's say it was instead submerged under water. What would be different? Okay, well, again, it's going into the water, so this is 1.33, right? It's coming from the polystyrene, which is 1.49. So the critical angle now becomes what? How do I clear that error? Okay. Inverse sine of 1.33 divided by 1.49. And so now we're looking at a critical angle of 63 degrees. Okay? 63. So again, anything at that angle or greater doesn't make it. But coming back to our discussion over here, if I actually had a beam coming in at 90 degrees, then this here would be 63, which makes that a 27, right? And that is by far lower than the critical angle. And so, yes, it would come out. And so this scenario is a little bit different. A cube of polystyrene underwater with a finger placed on top, you would actually be able to see it come out. The light is controlled. The light is bent a little bit different because it's underwater. A good example of this is your own eyes. Have you ever used your eyes underwater? You open them up in a swimming pool and you probably can see Clearly? Why isn't it very clear? What's different? The light, the bending of the light is controlled in part as the light goes from the air into your cornea. The difference between the air and your cornea is very important. And now you've changed it. You now have water next to your cornea. And that is a lot less difference in index and a lot less difference in the bending of the light. And then, of course, makes it harder for the other parts of your eye to control the light. And you can't control it enough. And so you can see kind of well, but I would say kind of fuzzy underwater because of the light there. Well, going back to these numbers then, if I work backwards, now that I know there is actually an answer, unlike the first time I did it, and I wasn't knowing if there was even going to be an answer, but now I know there will be an answer, let's find it. And so if this is at a critical angle of 63, then this has to be 27. If that is at 27, then I would get that angle. And so going to Snell's Law, going in, this is 1, this is sine of theta. Oh, sorry, we're underwater. 1.33, yeah. Okay, so we're going from water into the polystyrene. This then is the polystyrene, and this angle would be, what do I have over there, 27 degrees. And so I should be able to find the angle now, yeah.
So then would it be feasible for them to ask, like, so you have this angle incident in the water, the light coming from the air into the water, could they ask that to get your angle of incident?
Oh, are you saying we could probably put the block...
No, have the block under the water.
The block underwater, the whole thing underwater?
Yeah, because that's what we're doing here, right?
Yeah, the whole block is submerged.
Right, and then could you say your light source is actually from air into the water?
Oh, yeah, okay. Yeah, we certainly could make this a more involved problem. Sounds like a good test problem. Where we could come in from the air, into the water, into the polystyrene, and see if it can come out.
Yeah.
Right? That's what you're asking.
Yeah.
Okay. And another derivative of that same question could be, what if you have the water level right there? So the air entering the top comes in from air, and then can it get out over here? And based on the numbers we had up here before, the answer is yes, and then what would that angle be? I thought that's what you were going to ask me, but that's a good one too. That's a good one. But that's not the one they're asking. They're asking the one where the whole block is underwater, and that's why, underwater, that's why I put water there and the polystyrene there. Yeah?
Is there a condition of nearsightedness or farsightedness that couldn't see clearly underwater?
Yeah, exactly. Somebody who is nearsighted, their cornea is bending the light too much in the air. And so when they get underwater, which then it has a correctional effect the other direction, they may be able to see actually quite well. Yeah. I'm not sure how nearsighted that is. I'm slightly nearsighted. I'm like a negative 1.75. I know that's not even enough. But I would think, I don't know what the numbers come out to be, but you probably have to be very nearsighted for it to work that way. I should ask my mom. She's very, very nearsighted. Always has been. But then again, I don't think she likes to go underwater either. So she's the wrong person to ask. I can just force her under. Let me help you with the bath, Mom. Okay. But yeah, and it's also why animals that are amphibious will have a different eyelid or a different covering to their eyes as they go from looking at things underwater between looking things above. It's why we as humans can actually see very well underwater if we do. Yeah, all we need is an air pocket in front of us. And so a small amount of goggles or a bigger face mask doesn't really matter as long as there is an air to cornea boundary that is going to bend the air in the appropriate amount. So coming back to this number here, 1.49 times the sine of 27, then dividing it by 1.33, then taking the inverse sine of all of that gives me about a 30.6 degree angle there. And so that would be the angle that we talked about. Anything greater than that then would actually come out. Anything less than that would not come out the other side. I'll skip the last part of the question. I think you've learned the lesson because the next one basically says the same thing. What about carbon disulfide? Carbon disulfide, I think was listed, I hope it is, and gave the index. I'm not sure what it is. Ah, there it is. Oh, maybe this is worth talking about. No, it's a liquid. But it is N equaling 1.6. So it's more than the polystyrene. Ah, this is a good one. Let's talk about this one. This does have an important lesson. I thought we were going to be done with the lesson, but this is what would happen here. If you take a beam coming in and it's in an index of 1.6 going into 1.49, what happens? It bends away from the normal. And more than that, when it gets to this side here, we're in a small index going to a large index. What's the critical angle there? And it doesn't have one, exactly. Remember when we get a critical angle? What's the requirement of a critical angle? It bent away from the normal, right? We have to go from high to low. And so this thing, when it goes into a higher index, is going to bend towards the normal. It is never going to bend away from the normal. It's never going to have total internal reflection. And so it's not a matter of what angle does it. The answer is no angle does it. You never get internal reflection. Yeah, all right. So now I see why the author put that number in there too. See if you were kind of paying attention along there and what's the angle. All right, well, I got a couple more listed here. Let's try some more geometry. I like this one, number 35. They don't really give a picture of it, but I'll move back towards 35. But it is a common scenario you see on the road. Maybe you've seen it yourself. But have you ever been driving on usually a long, hot, straight road, and you look out in front on the road and look what appears to be water? Sometimes you call it a mirage. So some of you have, some of you haven't. But here's what can happen, and here's kind of the physics lesson as well as the numbers that they're going to put in here. If here is this road, and I'm sitting in the driver's seat here. Blue Ferrari, there we go. No, we got to change to red here. All right, all right. All right, so we're driving along in the car. And you look out, usually off in a distance. You can see what looks to be water on the road. It looks to be this rippling blue stuff. Why? Well, the key here was right here. The ground is black. You're maybe out on the desert. The sun is shining and it gets hot. Because going back to our thermodynamics, what do we know about air when it gets hot? Yeah, right, the molecules go faster, it expands out, there's more spacing between the molecules. Put that together with our optics we just did, what would that say about the index? It would go down a little bit, right? And so this index may go down from our standard 1.003 that we usually talk about for kind of room temperature, room density air, and drops down a little bit because of its higher temperature. And I think that's the number they give us. Let's look at this. It says, consider a common mirage formed by the superheating of air immediately above the roadway. A truck driver whose eyes are 2 meters above the road, where the index is 1.333. So from the truck driver's point of view, they're off the road, you know, it's not hot air up there, so the index, other than right above the roadway, is 1.003, and looks forward. She perceives the illusion of a patch of water ahead on the road, where her line of sight makes an angle of 1.2 degrees from the horizontal. So, in other words, this light coming to our truck driver, 1.2 degrees. Yeah. All right. It's okay. Women can be truck drivers these days. All right. But she perceives at an angle of 1.2 below the horizontal. All right. Find the index of refraction of the air immediately above the road surface. But to answer this, we need to go a little deeper. Why does it look like water's on the road? It's actually a reflection of the sky. This is actually a critical angle, a total internal reflection. Remember, the sky over here is blue, and so if the light comes down and goes from a high index to a low index, if the angle is great enough, what will happen? Total internal reflection, and the light will bend up. And so really, even though the truck driver is looking down onto the road, what they see is blue. In addition to that, the air being hot rises and the index kind of changes. And so with changing indices, you get kind of a rippling effect. And so not only do you see blue, but you see a ripple, and of course blue with ripples imply water. And so you think there's water out there. So you're lost in the desert, you're stranded, you look out, you're going to see water ahead of you. Keep walking. Unfortunately, the water will keep moving ahead of you, but maybe you will finally find civilization if you keep thinking there's water in front of you here. But there is no water, it's the sky above. And so that's where this comes from here. Now what are they asking for here? Oh, find the index of refraction immediately. Oh, so they didn't actually give me this. This was kind of my discussion about what it might be. But we can find out what it must be in order for critical angle to occur here. So again, going with n1 sine theta 1 equaling n2 sine theta 2. If we start in a high index and hit it at a critical angle, we must go into some lower index when we are refracting at 90 degrees. And so that is our N2. Now, since we know that you can actually then see the light at this 1.2 degrees, then I know that that must also be the corresponding critical angle. And so drawing a vertical line there, then this must be, or maybe I should put it over there as the incident angle, this must be that critical angle. And so this is my 90 degrees minus the 1.2. That's my critical angle. And so for this to work, my index N2 will have to be a little bit smaller And of course, just a little bit. Let's see what I get. Sine of 90 minus 1.2 multiplied by 1.0003 coming out to be, oh wow, 1 point, 1, 2, 3, 4, 4 zeros and an 8.
So the lower you get to the ground, the less heat needs to be there.
Yeah, at the angle, right. So, and that's why, good point, that if you look down the road and you only look, say, 100 or 200 yards, you're not going to get total internal reflection, and you're not going to see a blue ripple just a couple hundred yards in front of you. The farther you look, which is why you really need to be on one of these long, straight desert roads, they're easy to see then, because you have the heat, you have the long distance to look at. Yeah. And so there's when you get your index. Now, they don't bring it up here, but I thought this would be a good time to bring up what can occur for us. And maybe I'll even ask if any of you have seen this. Because the opposite of this is often referred to as a mirage. The opposite of this is looming. Let me change my picture a little bit. What if I reverse things a little bit, and I'll say, okay, here I am making the observation, and it is actually cool air down the surface and hot air above it. Now that's not normal, but it can happen. Normally, the sunlight hits the surface, warms the surface, then the hot air rises. As it rises, it expands, and there's our adiabatic expansion, and then it cools. So we're used to having air cooling up here and warmer down there. That's our normal process. But given where we live, that we have an ocean, the air may not be able to warm up because the ocean stays cool. And so about this time of the year, actually better fall than spring, but the ocean can be in the cool stage. I mean, what's our ocean temperature? 58 right now, about 58 degrees Fahrenheit. All right. So I would say the air right above it is somewhere probably around 58. Now, it's not happening today, although it is starting to warm up, but if the wind blows from the other direction, if we have the Santa Anas blowing, what can happen is the air can come down, it can compress, it can warm. As it comes over our mountains, there can be a layer of hot air coming across that is warmer than us down here. And so you can get this. Often happens, like I said, in fall where we get our Santa Anas and the ocean has already turned a little bit cool after the summertime. And the sky's clear. But what happens then if you've got an island out here? What happens to the light from, say, the base of the island? Now, I suppose it could just go kind of straight to me. Yep, there's the island, there's the base, no problem. But what else could happen with the light? And the person over here sees also the base of the island up here. And you have this kind of flat looking hourglass shape of the island. Anybody seen this? Nobody? Oh, good, a couple of people, yeah. Yeah, and so it is not that common, but usually I see it about once a year, usually in the fall time. You do need to be close to the water level, so unfortunately from campus, I think from campus here, I've only seen it one time. It was extremely warm and cold.
What about sometimes it looked really close? Like,
oh, and the closeness is also an effect. It's not in an extreme of this, but yes, the light is being redirected, and maybe I should wait till the next chapter, but it's being magnified, and the light is being redirected, just not this extreme. And that they can look that close. But they can also look that close just because it's clearer, and that has to do with how much water is in there. And when you look over any body of water, especially a cool body of water, moisture develops. Yeah, yeah. And so there's usually particles there, and then it cuts down on our visibility. But when that's gone, they look closer. I mean, I got to admit, sometimes, I mean, they look extremely close. Sometimes the oil, you know, barges or rigs or platforms, whatever those things are called, I mean, they look close enough. Unfortunately, sometimes people think they can swim to them. That's, you know, guy can't be that far.
Yeah.
Then the Coast Guard's out there all night looking for them, you know. I was just going for a swim. They look so close. It's only 5 miles out to the closest one. What's a 10-mile swim with currents in cold water? I can do that. All right, well, I'm going to put closure to this chapter because I want to make sure we have time to get into the next one. There are a bunch of good examples to do, but I think I kind of hit the first stuff. And I think you'll see that it's the easy stuff. It is apply Snell's Law and also geometry, and you'll be there. But I was waiting until 9:30, so we're there now. Let's turn the page here. Let's continue on from our discussion about these light rays and how they are controlled either by reflection or refraction. And let's control them then. Let's use this, as you talked about, a magnifying glass. Let's use them to make a telescope, a microscope. Let's talk about how a camera works. Let's talk about how our eyes work. All of these instruments, these optical instruments we like to say, control the light. And they all control it by either reflection or refraction. And so maybe just to start us off, I'll look at a mirror. Now, probably the least exciting mirror to look at is a flat mirror. But we'll start there. I'll turn it in a couple of angles so that you guys over here can see. But you will probably notice that as you look here, you will have a reflection, right? The light is being controlled. The light is being reflected off. If the mirror is curved, the reflections are still there. I think they can get a little more interesting if you haven't seen the lights in a curved mirror. But it too can form an image. The geometry is a little bit harder because the light's reflected. It can be curved in this way, which we'll call concave. It can be curved this way, which we'll call convex. They could even be big mirrors that do this, or this. And so what do you see? And why do you see what you see in these mirrors? And I'll start there. Then we'll go on to lenses here. But obviously today we'll just have enough time to do mirrors. And I'm not even sure we'll get past really the flat mirror. But that's where I want to begin here. So as I said, this last half hour I wanted to save for an introduction and a start into chapter 36. And again, if you've looked ahead here, you'll see that it is called Geometric Optics. And so we are going to take these two laws of our geometric optics, that is the law of reflection and the law of refraction, and apply them. Let's start with reflection. Let's start with a quick discussion about what I would call a flat mirror. A flat mirror means that the surface that is reflecting the light is a plane. It is nice and flat. I'll draw it this way. Here we go. Flat mirror. Okay, and so this is the mirror. Now obviously that's a two-dimensional drawing of really a three-dimensional situation here. But if you imagine it's me standing here drawing a mirror. What if I were to put something in front of the mirror? I will call this the object. But not a surprise, I have something in front of the mirror, right? This is my object. If you were to stand over here by the mirror, what would you see? Now, the boring one is, well, the light would come from the object to your eyes. Yay! All right? Anybody see the object? The light just goes right from the object to your eyes. But let's pause here for a second. How far away is that object? Am I closer to you, or is the object closer to you? Aren't I closer to you? How do you know that? What is the information telling you that?
I can see the object.
Okay, I would agree there's a couple of different reasons. One of them is if I stood in front of it, I would block it. Okay, so we have overlap. But I'm not standing in front of it.
Stereoscopic vision.
Yeah, and that's what I'm after, what we call our binocular vision, our stereo vision. Why do you have two eyes? What does the second eye play a role in? What's different between the two eyes and one eye? Right, and so if I may, I will put two eyes on this person. You making fun of my picture?
Why is he have three?
Remember, I'm grading your test this week. All right, but I don't know, does that do better? He's got more hair than me. Okay, all right. All right. But an important part for this whole chapter to make sense is to make sure before we go forward, you make sense of why do we have binocular vision? Why do we have two eyes? How do we perceive depth is important for our binocular vision, because what's going to happen is one beam of light will go to your left eye, another beam of light will go to your right eye. And by you learning over time the angles that are associated with the light, you begin to learn over time about depth perception. Now, granted, as you pointed out, there are more things to depth perception than just our binocular vision. There is definitely overlap. Another one is size. If usually if you saw an image of a car and a car is small in the image and you associate cars with being big, you would say it's far away. So there is the size, there's overlap, but and other reasons. But the big one I'm after is the binocular vision. That if I were to stand here, I would know that this chair is closer to me than that chair, because the angle of the light that comes into this eye gives me a slightly different image than the light that goes to this eye. And when I am close to something, that difference between left and right eye is substantial. Whereas something over there, the difference between left eye and right eye is very little, and my brain processes the difference between them, and I've learned about depth perception. And you all have. When you were little, you probably struggled with it. I mean, how many times have, babies had little moguls of teddy bears floating above their heads, and they reach out, not realizing that they're never going to reach to the ceiling for that. It's too far away. And you've learned over time, hopefully to the point that most of you now can drive a car, make a left-hand turn, and know how far away is that car and whether or not it is safe to make a left-hand turn or not. And I guess it's part of your driving test. Do you have depth perception? But some people don't have depth perception. In fact, my neighbor, great guy, retired. He's missing an eye, though. I should say the good thing. He actually says it's the best thing that ever happened to him, believe it or not. But when he was 4, he was cutting a rope with a knife, and it cut and poked him in the eye. Well, now he's 85, but he goes, you know what? It got me out of World War II. It got me a full scholarship ride to New Jersey Tech, and so he spent his whole life being he was an engineer for the city, and Anyway, so that's why he says it's a good thing. But he has no depth perception. A great guy. He always helped me. And so I was putting new shingles on my roof, and so I'm up there. I'll help you. He could not hit a nail. to save his life. I mean, he puts the nail in there and he goes, wham! Wham! And I just start laughing. He goes, yeah. He goes, I just cannot do anything like this. I have no depth perception. So it was cool. He just stood up there and handed me more signals. So it worked out. It worked out really well here. So we worked together as a team. But that missing eye just made it so clear to me. In fact, even when I go over to his house, I knock on his door. And I always look, because he tried to paint his house. Well, you got corners and no depth perception. I mean, he's like, it's good. Anyways, I got sidetracked here. But the point being here is that second ray is important to your depth perception. And if you don't realize that, realize it now, because it is those two rays that we're going to be talking about on and on again in this chapter to begin to understand how is an image formed after the light reflects. Because this is not the real part of the story I want to get at. The real part of the story is, what does this person see when they look into the mirror? And light will bounce off that mirror. They will bounce off, and it's not shown real well in my picture there, but doesn't the angle of incidence equal the angle of reflection? That is where the light going into this observer's left eye would go. What about their right eye? And I'll make it a little extra big just so I can draw my picture better. Obviously, those two beams are too far apart for these eyeballs. But that angle would have to equal that angle. Here's why. Let's say these two rays did go to left eye and right eye. What would this person then perceive? You would perceive this beam coming from back here, this beam coming from back here. See where they cross right there? That's an important part, because that is how your brain is functioning to figure out where an object is. And so as this person looks into the mirror, they will have the perception of an image. The light will have that appearance of coming from that spot. And so again, I'm sure all of you have done that, and just in case you didn't, I brought the mirror out here. But if you look at this object, you will see not only the object that is in front of the mirror, but don't you see an image of it? And so the light does, say over here, bounce off and go that way. And your brain would process that and project it back. And what I really wanted you to point out here is that notice where your brain would say the image is. Would it say the image is on the mirror? Kind of like a painting? No. Where does the light appear to be coming from? Actually, back here. It is why, if you haven't noticed, there is another rod behind it. Because if you look, I'm hoping that the placement of this rod that is behind is actually far enough back exactly to match where the image of that one appears to be. And so the mirror is deliberately cut in short so that the height of the one that is literally back here you can see, whereas the stuff below is the image from the one in front. And if you then move it, it just looks weird. Okay? And so this first one, and the easiest one, is a flat mirror showing you an image can be formed. And here's going to be our goal. For the whole chapter, our goal is going to say, if the light goes into the mirror or the lens, how is it redirected so that there is a left and right eye, project it back, that's where the image is. And so we're going to be asking ourselves things like, does it form an image? If it does, where is the image? How big is the image? And so let's talk a little bit about this one. This is our first one. This is the easy one, if you will. This is the flat mirror. We can do geometry and the law of reflection. Let me draw it again here. If I draw a mirror and an object, I'll draw a dotted line that's horizontal, so it also represents the normal. I will draw two rays. Now, I won't even draw these same two rays. Let me just draw any two rays, because the first ray to draw is probably the one that hits straight on, the normal. Where does it go when it bounces off? Straight back. And so here is my object. How about the ray that hits, say, here? Well, this is some angle theta 1. It will bounce off, and that would be theta 1 also. That ray traced back to that ray means that if somebody was standing over here, and this was the ray that went to their left eye, and this is the ray that went to their right eye, they would perceive the light coming from right there. And so that is the image. To be a little more specific, and I heard one of you say it already, this is what we would call a virtual. Doesn't look right.
You have a T.
T-U-A-L. Virtual image. And so there is my virtual image. What do I mean by virtual? Yeah, the light, was it ever really coming from that spot? So this right here sends the light, redirects it to your eyes, gives it the appearance of coming from back here, but was the light ever really here? No. So that's what we call a virtual image. And I would say most of you are familiar with virtual images. I think that's why this one here, although we're going to run out of time to talk about it today, always catches people's attention a little bit more, because this one, the light actually comes in, hits the curved surface, or light comes out, hits the curved surface, gets redirected into a point, and then spreads out from that point. So as it spreads out from that point and goes to your eyes, you trace it back to right here. Was the light really there? In this case, the answer is going to be yes. Here, the light hits, gets redirected to right there, and then spreads out. And so maybe I'll wait more on that, but that's going to be called a real image, just to compare it to a virtual image. They're both images, because that's not where the light actually started from. But whether the light really groups here or not is an important question. And so that is called a virtual image. Let's give some symbolism here. The distance that the object is from the mirror, we like to call P. This is the object distance. The distance the image is from the mirror is what we like to call Q. And so we'll use this notation plenty of times throughout this chapter. And my question for you would be, in this scenario, how are those related? And you say they're equal, and I ask, why? I'll even answer it. Yes, they are equal, but prove it to me. Why? Because it won't always be equal, but they are in this case.
Because the mirror is straight.
Yeah, it does have to do with the fact that the mirror is flat. We could go through a little geometry, and we shall here. Let's do this. This was the law of reflection. So there's the physics. As we get into geometry, that would tell me this angle is the same, because that is a vertical angle. It would then tell me that this angle is theta 1 as well as that angle is theta 1 because, again, geometry of alternate interior angles. This is at 90 degrees, and so maybe the first thing I can say is angle, angle, and then these angles would have to be the same, wouldn't they? And so that would show me that two triangles, and maybe I should even color code them. I'll do green and red here. So this triangle in red and this triangle in green have all the same angles. But they're even more than that. Don't they share a side there? And so two triangles that have an angle side angle or angle angle side, we say they are congruent, right? So if they're congruent, what does that say about this length, Q, and this length, P? They're equal. So after a couple steps of geometry, we've got P equaling Q. Yes. So, how do the lengths of them compare? They are the same. And you can see that for a flat mirror, that would always be the case. Oh, let's keep going with this. Because what I have here is kind of a drawing of a single point. The reality is, when you take an object, don't you have height to it? So you could imagine maybe this was a calculation or a picture of the top of it. What if we did that same thing for the middle of it and the bottom of it? And so if we change our picture into that, something that has height, then the top of the arrowhead would be right there. But what about the middle of the arrowhead? What about the light coming from there? Yeah, and again, I think from the same, and let me not draw all the rays, but wouldn't it be right there? What about the bottom of the arrowhead? It'd be right there. And so wouldn't I get an arrowhead that looked like that? So if I call this the height of the object, and I call this then the height of the image, so we like to use an H prime for the height of the image, how do those two compare? And they're the same here. And so H equals H prime in that case. And so again, notice what I'm doing. Notice I'm applying the laws of our optics, in this case only reflection, and some geometry based on the shape of the mirror, and I have gotten my first answer. What does the image in a flat mirror look like? Because what if we switch this up? What if instead of having a flat mirror, we change it to a concave mirror? What are you going to see there? Well, let's do the same thing. A little harder, I must say, because things are curved instead of flat. In fact, it probably would serve well to maybe do a quick experiment with a series of light beams coming in and taking and hitting a mirror. And I don't know if you can tell from your distance. This is the one I've been showing you. Polished flat mirror, polished curved mirror. And this is curved just a little bit inward, concave. What happens if I put then a concave mirror there? I get And should I close those, or is that? You can see that? Maybe I'll angle it up a little bit too. But well, I'll lose the simplicity of it.
Put it further.
Oh, over here? Too far. Okay. All right. There we go. And so.
Harder at that single point they intersect.
Is it what?
Is it harder at that single point they intersect?
Oh, yeah, I suppose so. I mean, if I were to put my finger right here, I guess I would say I'm getting hit by 5 beams. And so that would be warmer than putting my finger here, which only gets hit by 1 beam, or even here, which only gets hit by 1 beam. Yeah, yeah. And so this is a focusing of the light energy here. But of course, what I do want you to see is that I have what we would call a focal point here. I have this point right here that I'll call F, right? I have a focal point. Now, you might ask, where is that focal point? But I think you could see that it would vary on how much the mirror is curved, right?
And the angle that the light is coming in at.
Well, okay, the angle that it's coming. But in my case, isn't the light all coming in parallel? All right, so at first, let's just talk about that. If I had light coming in parallel, here, and here, and here, and here, and here, but this beam is like that. I'll draw the lower one too. It's bouncing off and going like that. But again, this gives me a chance to introduce you to what we're going to call the focal point. This is the point where the light would all come together when it started off in a parallel sense. But this mirror is curved. This mirror is part of a circle. And maybe it's hard to tell. I think it's easier to tell this one is part of a circle. This is half of a circle, so it's a hemisphere. But can you see this curve would be part of a big circle? So wouldn't there be a center of the circle? Where would that be in this picture? Is that the center?
No.
No. Why not?
It's too close to it.
Well, if you draw a normal from a mirror, and it's part of a circle, where does that normal go? You're right. That normal is the radius, isn't it? Okay. So the normal would meet over here. Let me call it C for center of the circle. Right? And so again, I wanted to point out here that we've got 2 interesting points. One is the center of the circle and one is the focal point. They are not the same. Right? I know that because of the law of reflection. That was really my question, that this angle has to equal that angle. But shouldn't those be connected mathematically? Well, let's give it a try. Where is the focal point compared to the center of curvature? Well, hopefully you're seeing here at the very beginning parts of this that they are definitely not the same place and that the focal point is less than the radius. Fair enough? But how much less? Well, let's do a little geometry. Some of you might even remember from 102 that it comes out to be half as much. It does only if we do a little approximating. So we're going to do a little bit of approximating here, but it works out really well here. Let's just say, for the sake of discussion, that this angle, which I'll call theta, and so this angle here that I'll call theta, is relatively small here because I'm going to draw a couple of triangles. I'm going to draw a red triangle. And I'll draw a blue. I'm sorry, green. I already got blue up there. I'll do a green triangle. So if I look closely at my geometry, let's see, this angle here would be theta, right? Because I've got two parallel lines, and that's alternate interior. And then this angle in green, wouldn't that be 2 theta? Because again, angle of incidence equals angle of reflection, so that's 2 theta. And so this angle there, 2 theta, has to equal that angle there, which is 2 theta. If I do a little geometry here with my red, I can say, what is the tangent of theta? Well, the tangent of theta would be this vertical height, let me call it y, over this horizontal distance. Which, here's where I'm going to do my first approximation, which I'll do a second one, but they're actually one and the same. But I'm going to call that the radius. Is it quite the radius? No. Wouldn't that little difference right there? Okay. So if this is not curved too much, which in this mirror, I would say that's probably pretty close to being true. I look at this mirror, the center is probably there. And the difference between something at the top of the mirror and the bottom is that. So, is it exactly right? No. But a very useful approximation. It's going to make our math a little bit easier. Some of you will go on and take upper division optics, and you will then worry about that slight difference. But for us, this is a good place to start. So I'm going to call that R. I say that because if I go to the green one and say, let's look at the tangent of 2 theta, what would it be? Yeah, y over this f that I'm looking at. Okay, and so there's my f. Now again, same thing can be said that it's not really f, is it? It's actually a hair less by that same amount. But again, if you're willing to accept not much curvature to it for the same reason in the one before, we'll have an approximation. I'll do you one better. We did this way back. What if I have, say, sine of theta, and the angle is small? Do you remember us saying that that's approximately equal to theta? When we did like the physical pendulum? Yeah. And then tangent would be the same thing. Tangent of theta would be approximately theta also for small angles. And that is going to help us a lot. Because if we're talking about angles that are not very big, then I can replace tangent theta with theta. And that approximation really is the same approximation I made there, because that means this angle here is not very big. And if you remember the pendulum, we said that was accurate to about 5% if we were less than 30 degrees. So again, not exactly right, but a reasonable approximation gives me what? In place of theta, I can put y over r equals y over f. The y's cancel off. If I cross multiply, twice f is equal to r. Or put another way, f is half of r. And so some of you might remember from that last week in Physics 102 when we did our optics that there is a focal length, and that focal length is half the radius. And I said that, hey, when we get into Physics 123, I'll show it to you why it works. And so here we are today. I'm showing it to you why it works. Okay? And so it's half that radius of curvature. Yeah?
So just an out there question. If you happen to be standing at the focal point, does that mean that you won't see anything?
No, it doesn't mean that. But that's a longer question than I can answer in the time that's already passed. So come on up if you want to talk, but we'll get to that next time. So anyways, we'll stop there. Your job, of course, is to go back and get started with your optics this weekend and then look ahead in this chapter, and we'll get started on our geometric optics and our mirrors and our lenses.